Today's episode, everyone, welcome. We are interviewing the amazing and super knowledgeable Raymond Pierrehumbert, professor at Oxford. Professor, thank you so much for being here. We have a lot to talk about. Could you please just introduce yourself and tell us a little bit about you?
Yes, I'm Ray Pierrehumbert. I work on all aspects of planetary climate, from Earth's climate onto the climate of solar system planets and the climate of these thousands of newly discovered exoplanets. And what makes it possible to do all of this sort of in a lump is that it's the same basic physics that applies to all of them, just but with in different combinations and so forth. So it really speaks to the universality of physics.
hmm And what got you interested and started in this? Was it when you were a little kid? Was it when you were attending school, work, or what was it?
Well, it's actually a long evolution. Of course, I've been in this subject for 50 years or more if you count when I first started getting interested in stars, planets, and fluids. But actually, I started off by being interested in fluids and the flow and all the amazing patterns you get from the flow of water and things like that. And you can see this with little kids, even toddlers. They just love to play with water and see how it flows. It's endlessly fascinating. And so I studied this kind in addition to regular physics. I studied fluid dynamics for quite a long time, but and started applying fluid dynamics to Earth's atmosphere, and then to atmospheres of other planets, and then I started adding in additional physics as I went on, and got exposed to different problems from my colleagues here and there, and when exoplanets were discovered, well, that was a whole new sandbox for the kind of physics I'm interested in. So I jumped right on it, and that was, I guess, about almost 15 years ago now. I started working on exoplanets.
Tell us a little bit about exoplanets. I don't know much about them. I'm sure that the audience would also be very curious to know a little bit more about them and what makes their, I guess, all the physics about them and the things going on over there so different and unique.
Well, so exoplanets are planets around stars other than the sun. And up until about 30 years ago, when the first exoplanet was discovered and confirmed, we really had no idea for sure whether we were the only solar system or planetary system or planets in the universe. We had reasons to believe there were other planets out there, but no direct confirmation. But then the technology advanced by about 30 years ago to be able to actually detect the signature of planets around other stars. And now we know thousands of them. And they have a much greater diversity of climates and characteristics than what we have in the solar system. For example, we have rocky planets that are so close to their stars that they have a permanent lava ocean on one side, and then the other side is actually quite cold. Those are called lava planets. And there are planets that are a little bit like miniature versions of Neptune, although they have more rocky component than Neptune. There are planets that are tide locked to the star, like the moon is tide locked to Earth. So there's a permanent day side and a permanent night side, and dozens of other special things. Planets where the thing that makes snow is quartz. It snows quartz, or even sapphires on some of these planets, and just endlessly fascinating physics.
That's so interesting. There's a planet where it rains actual crystals.
Yeah, well, it's actually more like snow since it's a solid form, but
Oh, okay. So
yeah,
it's the
yeah,
liquid form of that
yeah,
same.
yeah,
Oh,
yeah,
wow.
yeah,
Super
yeah.
cool.
Yeah, but there are other planets where there's liquid mineral rain, like sodium, liquid sodium can rain out on some of these lava planets.
And how do we detect that? How can we say for sure? Let's say somebody who maybe isn't as well versed in this. How does a scientist or a group of or collective of scientists, let's say at NASA or Oxford University or wherever, how do they come to that discovery? How do we pick up the chemical signatures being produced?
So some of the things I've been talking about, like sodium, are fairly difficult to detect by telescopes, and so a lot of that comes from the chemistry that we know on Earth that we can do in the laboratory and extrapolate that to the conditions we believe exists from theory on these other planets. But other compounds we can actually detect on exoplanets by various kinds of spectroscopy, the kinds of light that they absorb and emit. So for example, one of the gases everybody's interested in is carbon dioxide and carbon monoxide. And the way we detect that or water is similar to the way we would detect some of these mineral vapors like silicon dioxide, which is beach sand or quartz. And basically, if the planet goes in front of its star, in parts of the spectrum of the starlight, colors of the starlight wavelengths, where the atmosphere is a good absorber, say where CO2 is a good absorber, if it has CO2 in the atmosphere, the planet looks a little bit bigger because you're seeing the sort of dark atmosphere blocking more starlight. And in parts of the spectrum, parts of the wavelengths where the atmosphere is very transparent, the planet looks smaller. And so it's like putting the planet in a spectrograph. And you can see the characteristic signatures of absorption. And the other related spectroscopic method is that when a planet goes behind the star, then it blocks the infrared radiation that's emitted by the planet, and the characteristic wavelengths at which different molecules emit then tells us something about what the chemical composition is in the planet. It's a little bit like the sort of Bunsen burner flame test. You put a little bit of something in your almost transparent blue flame on a burner, and if it has sodium in it, it tends to glow a kind of a bright orange. We do that sort of thing, except mostly we do it in the infrared, not in the visible range. And what's been really transformative in our ability to do this for relatively small planets is the James Webb Space Telescope, which has just opened up a whole new field and being able to see what's going on in planets of Earth size or a little bit bigger.
I wouldn't have thought of it that way because that actually reminded me of a conversation I had with somebody who talked about how we can use, specific color patterns and like thickness and thinness to see the differences within like an internal system, like veins or in the brain, skeletal or muscle structures. And it's so weird that the same thing can happen from the outside, viewing it from a planet. Like you said, carbon emits a darker atmosphere that's viewable, so that it's so wild how everything is interconnected on one level or another.
Oh, and it's the University of Physics. I mean, the things that we do are rather similar to a lot of medical imaging. It's all a matter of seeing how some wave or some wavelength of light interact with the matter you're studying, and that works whether you're studying someone's brain or whether you're studying a planet, hundreds of light years away. The difference is we use the planet itself as the light source when it's emitting infrared, or we use the star as the light source instead of some kind of X-ray machine that you have in the laboratory or in the medical office.
Yeah, it's interesting. That's one thing that one of our previous guests had said. I'm so sorry that I'm blanking on his name right now, but but it that's so fascinating to me. But you did bring up carbon, and I did actually want to speak to you about carbon. And obviously, our entire world relies on carbon. We produce carbon. Tell us a little bit about how carbon, along with all these other molecules and chemicals, started, what happened, where did they come from, and what has led to the building blocks of life.
Yeah, so actually, maybe I'll start very quickly outlining why carbon is so interesting, and there's a biological part of it and a non-biological part of it. Although the non-biological part does feed into why our Earth is habitable. So the biological part of carbon is that it's a fairly unique atom in terms of being able to bond together, make compounds with many other different elements, and to build long chain complex molecules. And that has to do with just the arrangements of its electrons. Uh, and uh, and so life is well, the main component of anything living is actually water, but the thing that actually makes it alive, the thing that allows it to move energy around and build DNA molecules is really mostly carbon. And the next thing after that we're made out of, that life is made out of, is nitrogen. But we have about 10 times as much carbon as we have nitrogen. So carbon is really king. And it plays roles in almost every imaginable kind of biology. It's how we store energy in the form of carbohydrates. It's an essential component of the sugars that are part of DNA. It's like a special kind of Lego block that can just assemble itself into very organized structures. And it's important that the bonds it makes be strong enough to hold together so you can make persistent structures, but not too strong. So there are lots of mineral elements like silicon that have somewhat similar features in terms of what they can bond with. That they make crystals that are hard to break apart, and so in order to do things with life, to build enzymes and have the enzyme break things apart, it helps to have a bond that is not so strong that you can't pry it apart. And so carbon is the only molecule we really know that can do that. Nobody has thought of a way of carbon is the only atom we know that can really do that. And of course, there's a lot of speculation about silicon-based life because silicon does have an electron structure that's a little bit similar to carbon, but it actually needs much higher temperatures to build complex structures. And there's a question whether you can actually build the kind of complex structures that carbon does, even if you have high temperatures, because high temperatures also tend to, break apart long chain things. But carbon is really special to life because of the number of compounds that it can make. But it's also important in terms of what makes a planet habitable. It's the main temperature controlling gas, the main greenhouse gas in a planet in the form of carbon dioxide. And it's the natural carbon dioxide cycle on Earth that has kept the Earth habitable almost without fail for the last 4 billion years. There are all sorts of feedbacks and that control the amount of carbon dioxide in the atmosphere. And of course, it's what causes global warming. It's the main thing that causes global warming is release of carbon dioxide by burning fossil fuels is what's changing our climate. And we have massively disrupted this natural carbon cycle that has been keeping the Earth habitable for the last 4.5 billion years. But so that's the story about why carbon is of interest. We can come back to some details of that, but maybe we could go back to where carbon comes from. Would you like to do that now?
Yeah, I would love to know about how
Yeah,
carbon started and where it came from.
yeah,
Absolutely.
yeah, yeah. In the beginning, you know,
In the beginning.
in the beginning, it wasn't the word, or if there was a word, the word was spelled out in just hydrogen and helium. So, right after the Big Bang, in microseconds after the Big Bang, or milliseconds at least, essentially all of the universe was composed of hydrogen and helium because those are the particles that sort of coalesce out of this primordial soup of elementary particles. And About 20 minutes into the Big Bang, there was this short era where you could form somewhat heavier elements by fusing hydrogen and helium. But although you think of the Big Bang as a very energetic event, in fact, it's not energetic enough to form carbon. So you form just a tiny trickle of a few elements like lithium and I think beryllium and boron, but actually very very tiny amounts. The universe is still like 99.9 whatever percent hydrogen and helium at that point. And it's not until we get to the first stars, roughly 500 million years after the Big Bang, that you have environments that are energetic enough to actually create carbon. In fact, it's not in the first generation of stars that this happens. It's so a star like the sun is not making any carbon. A star like the sun has inherited some carbon from dead stars, but a star like the sun, which is called a main sequence star, has as its purpose in life and its energy source fusing hydrogen into helium. So it's making helium. At some point, it will run out of its usable hydrogen fuel, and then it will actually undergo a reorganization and puff up into a red giant star. And It's at the stage where it turns into a red giant that it starts to actually fuse helium together and make carbon. And so this process started in very massive short-lived stars about 500 million years into the age of the universe. And all the carbon in the universe, and there's been more and more of it accumulating over time. All the carbon in the universe has been made from dying stars, from stars that are undergoing this later stage. You make some in supernovas too, but you can make a lot of carbon in red giant stars, which is what our sun will turn into eventually. And red giant stars blow off a lot of mass, so they're like dandelions. It's like they're like dandelions seeding the universe with heavier elements, including iron. But carbon is the first thing you make uh, past the hydrogen and helium in these stars. And it's I think it's often been said we are all made of stardust. We're literally made out of stardust because all the other things we're made out of. I mentioned nitrogen, and then phosphorus is also important. The All those other things that go into what we're made out of, they're also synthesized in these dying stars.
That's a lot, but it makes sense. The sun what was it? Nitrogen and hydrogen. What was that again?
Well, the sun right now is not making any of that stuff.
Hmm.
The sun is just making helium from
Helium. Okay.
it's just making helium. But in about another 4.5 billion years, the sun will run out of its usable hydrogen fuel. And then it will expand to roughly the radius of the Earth's orbit. That's the ultimate habitability crisis,
Well,
and it will turn red, but it will also put out like 1,000 times as much energy because although it's dimmer in some sense, I mean not dimmer, but it's redder, which is usually means it's less hot, and it is less hot on the surface. It's so much bigger that in the aggregate it puts out more energy. It won't actually vaporize the Earth if unless it engulfs it completely,
uh
but it will melt the Earth more or less down to its core. So that's bad news. But you don't have to lose sleep over it
yeah,
because
we
it's
won't be
another
here.
format.
We
Yeah,
won't be here.
somebody might be here if we're lucky, but we've got plenty of time.
Yeah.
But it's at that stage. It's at that stage when a star like the sun turns into a red giant that it actually starts to make carbon and also some of the other heavier things like nitrogen and so forth.
And so that is the basis for life. Carbon-based life forms. That's where
Yeah.
that term comes from.
Yes. Yes. And
So,
also, I mean, another reason life has kind of evolved to use carbon as opposed to possibly something else that might be useful as a backbone. Another reason is that given that carbon is the first thing you start making when a star dies, when one of the more common kinds of star dies, there's a lot of carbon in the universe. And there's also actually a lot of oxygen, but carbon actually plays a role in the fusion sequence that gives rise to oxygen too. So it's even playing a role to why we have the oxygen that we breathe, which has been split off from carbon dioxide, but also why we have the CO2, which is carbon and oxygen hooked together.
that actually leads to the question I wanted to bring up because I know that life, obviously, we're all made of carbon, as we just stated. But how did that whole process start? I understand that you said that during the formation of the universe, during the Big Bang, that there was obviously carbon not being made. It only started being made 500 million years after the creation of the first, you know, the
Yeah,
universe and the first
after
stars
the
and
first
everything.
stars lit up. Yeah, yeah. So, but
But
how did
how does that lead us to where we are today?
Yes. Well, actually, at the stage we're at in exploring planets around other stars, exoplanets, we're still trying to understand how these sort of lighter elements, like carbon dioxide, carbon compounds, are actually delivered to a planet. What determines whether a planet has an atmosphere, whether it keeps it, what's the diversity of different kinds of atmospheres, and so we're far off from actually being able to say observe the early stages where inorganic carbon is turning into life. But even on the early Earth, where we have a lot of data from rocks, minerals, and so forth, and we know what the early environment was like, there's been a lot of progress in understanding how things like amino acids, the building blocks of life are created. In some of the recent studies of comets, and asteroids, it's actually been found that these lifeless rocks have most of the amino acids on them that are the building blocks of life, plus a lot that we don't actually use. And so you can make amino acids promiscuously all over, even in the airless space. And it's easy. So it's easy to make amino acids, and the people doing origins of life chemistry have been able to figure out how these, start to hook together into biologically interesting molecules, the precursors. It's interesting. You have to get nitrogen into the system, because to make information-bearing molecules, or proteins, which are the basis of enzymes, you need nitrogen in there, not just carbon. But it's hard to break up the nitrogen bond in N2, which is what the nitrogen in our atmosphere is made out of. So that's made by energetic ultraviolet breaking up nitrogen. And ironically, most of the pathway for getting the nitrogen into the system is through hydrogen cyanide, a deadly poisonous substance for life as we know it, at least for mammalian life. But so while there's a sort of a natural tendency for molecules to group together into things that are interesting looking precursors of life, we don't know how it made that step from the most common abiotic amino acid chain to the first, say, functioning cell or enzyme. The life that originated, the last universal common ancestor, was so good it kind of wiped out any precursor. And so we have this vast missing link between abiotic carbon world and the simplest forms of life. And so we don't have any idea whether that missing link step is very common, or whether we are very, very lucky and we're the only ones who have made that step. But an indication that it might be fairly common, that first step to life, is that the first signatures of life on Earth occur in extremely old rocks that are barely older than that are barely past the time when the crust of the Earth solidified. So whatever was going on, life emerged very, very quickly on Earth. The oldest life is like 3.8 billion years old, when the Earth is around 4 billion. It's roughly 4.5 billion years old. So the life happened fast, and we only have one example, but it gives us hope that maybe it was not an extremely uncommon sort of event. But
Yeah, that's not something I've ever actually thought of, or I think I've ever heard anybody bring up the fact that the step to our ability to exist, our life form, the path that, of carbon based life was so good that all the other precursors went out. If
yeah.
there were precursors, do we know if there were precursors, or is,
Yeah, because there's none left. There might life might have arisen in many different forms, and one indication, though, is that all life uses amino acids of a certain handedness. There are left-handed and right-handed amino acids, and we have inherited without fail the same handedness. All life on Earth has inherited the same handedness from the last universal common ancestor. Whereas you might have thought that early there might have been competing forms of life that used the other handedness, but there's no trace. If that happened, there was no trace, and evidently the handedness that we all embody, meaning everything living on Earth, was the life that won out. Or maybe just for random reasons, it was the life that got started first. But yeah, we do. But not only don't we have any trace of earlier forms of life that might have gone extinct, like we don't know the Neanderthals of the cellular world. This is one way of putting it. Not only don't we have a trace of that first life, but the enzymes that make life work now, that allow us to breathe, that allow plants to fix nitrogen from the atmosphere, make their own fertilizer and nitrates and so forth. Those enzymes are incredibly complicated. They're almost more like nano machines than just molecules, and so we don't really have a trace of what simpler enzymes were there originally, that might have been stepping stones on the way to building these enzymes that make life work, because life just got so good at using these complicated enzymes and making them that there was no survival value in keeping around these earlier enzymes, and they're not preserved in the geological record. And so that's been one of the challenges in understanding how you got from this soup of carbon, nitrogen, oxygen, and phosphorus and sulfur, carbon dominated, in an aqueous environment with water, to the simplest enzymes that could make life like chemistry work.
It's a lot. It's a lot of information to know, but that idea that there could have been a precursor, I've never had that thought or possibility. I thought there's maybe one specific way which life can exist, that which is the form of life that we know on Earth, as we're the only planet that really has any life form aside from maybe microbes or like amino acids, as you said earlier. And it's interesting to see that there could have been a possibility, like the way you said Neanderthals of this chemical age that we don't have any examples of. Maybe that might be out there. We just don't know what we're looking for. It's
Well,
it's
yeah, this is one
fascinating.
reason why it's so exciting to look for life on other planets. I mean, especially if we were to find life, even microbial life. Microbial life would be perfectly interesting because, if we found microbial life, very simple life on Mars or on Europa or on Enceladus. Uh, that's life that we could actually get and bring back into the laboratory. And the first thing people would ask is, does it use DNA or some other information bearing molecule? Because all life has to have some kind of information bearing molecule that can reproduce itself, but also mutate and evolve. Does it use DNA, or for that matter, does it use the same handedness of amino acids? Does it use amino acids at all? It probably
Hmm.
does, because amino acids are such a prevalent building block. They're just everywhere. The amino acids out on the comets have random handedness, unlike living amino acids in Earth life. And so, the first thing you'd ask, probably, if you found a microbe on Mars, is what's the hand? Well, does it use amino acids? Probably yes. And what's the handedness? Because it would be kind of bizarre if Martian life used the same handedness of amino acids. That would sort of suggest that life started in one place and was seeded from some central mother lode of life that got to various other planets. But
Hmm.
that would be exciting. It will be a little bit hard. It will be very hard to, if we ever do detect signs of life on exoplanets, since we can't bring it back into the laboratory, it will be very, very hard to say, anything about its handedness. Or we might be able to guess whether it uses amino acids by the kinds of chemicals it synthesizes.
Do you think that would be an intelligent idea to bring back any form of microbial life back to Earth?
Well, the general thought is that the environment in which that microbial life evolved would be so different from Earth that the chances of it actually being able to interact with Earth life are very slight. Right, but there is a whole uh, apparatus, and NASA has someone called the Planetary Protection Officer, which is, I think, it's a great job title. There's no uniform that goes with it, but you can think of Doctor Who
It's
or
a pretty
something. But
cool job title to
we have
have.
a cool job title, and that's a two-way job, because the idea is to keep life from other planets being brought back to Earth without having them contained and controlled, but also to prevent the contamination of other planets with Earth life, because probably some kinds of extreme Earth life, if it got to Mars, would actually be able to survive on Mars. And then down the road, if we do find life on Mars, we have to ask: is that because we contaminated Mars, or is it because life evolved along parallel ways, or there was a panspermia, so seeded from multiple places? And there's always a lot of tension with planetary protection officers on bringing things back to Earth, because they would like to sterilize the heck out of everything, and then we have no chemicals left to look at.
Yeah, it's a fair point.
Finding this happy medium between protecting the Earth from rogue viruses and actually having something you can look at. like
And
there have been sample return missions from comets that have brought samples from comets back to Earth, making having the ability to actually look at these organic molecules without having sterilized them to heck.
what
And
what have we found on those comets when we
well,
brought those samples back?
yeah. So the main thing, the most exciting thing, which is the thing I mentioned, that they're just full of amino acids. All the amino acids we all but serve two or three of the amino acids that life uses on Earth, plus a whole lot of amino acids that we don't use. And there lots of long chain organic molecules are there, and these are probably synthesized by interaction of ultraviolet light with chemicals in the substance of comets, carbon, nitrogen, so forth. And because they're out in space, once they're made, they don't degrade. There's nothing to eat them up, decompose them very easily, and so forth. But I'd say that's the most exciting sort of thing, that in terms of the sample returns. But also things like it's, atoms come in different flavors. Like carbon comes in three stable in say carbon 12 and carbon 13, which are both stable. And carbon 14 is radioactive. It's what's used in radio dating. And looking at the isotopic composition, the ratio of different isotopes, different weights of an element, can tell us whether it has the fingerprint of, say, carbon on Earth. So if we want to know where our carbon came from, and you have a theory that our carbon came from carbon or methane in comets that were crashing into the early Earth, looking at this isotopic fingerprint, this chemical signature, is part of how you do that. So there's all sorts of stuff like that that's been going on also.
Do you think any of our species would be able to live on Mars? I mean, I know there's some microscopic species that we have, like tardigrades, things like that, that can survive through the vacuum of space. But if there was, like, let's give it an example, some sort of maniac who had all the money and power and space travel capabilities in the world, if you were able to drop off any forms of life on Mars. It's the closest example and the most habitable planet aside from ours in our solar system, at least to my knowledge. What do you think would be able to survive and potentially, grow and develop over millions and billions of years?
Well, among other things, and I'm somewhat just speculating here, but there are very slow growing bacteria, and archaea, which are bacteria-like thing, geobacteria, that live a mile under in rock, a mile down deep. And they grow very, very slowly. They can make their own water out of hydrated minerals in rock. And if you go down a couple hundred meters under the surface of Mars, it just wouldn't be all that different from conditions on Earth. And so I would find it hard to believe that our extremophile geobacteria couldn't actually survive and propagate, if they managed to get down. They were inoculated, like with a giant syringe or oil well, down deep into Mars. Whether any Earth-like life could survive and reproduce on the surface, which is very cold and very dry and at low pressure, so any moisture would tend to evaporate and desiccate the critters. That's a bigger question, because it's a more harsh environment even than the Atacama Desert. You do have bacterial life in the Atacama Desert, which is maybe the most Mars-like place on Earth, but Mars is yet harsher still. But as for people, of course, people could build an environment on Mars, but it's still a place that would need a lot of technological support in order to keep an environment going. And so I think the expense of sending any significant number of people to Mars and making a habitable environment, it's just not where it's worth spending the money right now. We learned so much from robotic probes to Mars, that really our Martian exploration has very little to gain by sending people there and building a habitat and spending trillions of dollars on a Mars shot program just to send a few people to Mars. So, but Martian exploration robotically is getting better and better all the time, and we are learning a huge amount from that.
At least the Atacama Desert is on Earth, so there's a
It's on Earth, and
possibility that it could rain, and there is animal life that does live there, so it's
yes,
not like
yeah, and
completely
also
desolate.
a lot of astronomers live there.
Yeah,
The
that's right.
It's in fact the so I mentioned the James Webb Space Telescope, which is out in space, but the Atacama Desert is maybe the closest thing on Earth that we're to actually being in outer space. It's very dry. You're above a lot of the atmosphere, and so the giant ground-based telescopes and also the giant radio telescope ALMA, which we use to image solar systems that are in the process of being born. That's out in the Atacama Desert also. I mean, Antarctica is the other sort of place that you can get cold, dry air, but it's because you're on ice. It's logistically a lot harder to build something big there than it is in the Atacama Desert.
Is Hubble still active? Is
Oh
Hubble
yeah, Hubble.
telescope still active?
Oh yes, Hubble is still active and still being used, and it has a smaller mirror and it doesn't cover as much of the infrared as James Webb, it's not as it's not as essential for the observations in infrared anymore. But Hubble has the huge advantage that it actually covers the ultraviolet part of the spectrum, which James Webb doesn't. And Hubble is our only space-based telescope now that can observe planets and stars in the ultraviolet, which is very important for all sorts of reasons. And we can't really do ultraviolet astronomy from the ground on Earth, even at the Atacama Desert, because the ozone layer and even oxygen in the atmosphere absorbs essentially all the ultraviolet that's astronomically important.
Mhm.
So until there's a replacement ultraviolet observatory, Hubble is the only game in town. But even for infrared, given that time is very precious and in short supply
Hmm.
on James Webb, people are still using Hubble even in the ultraviolet part of the Sorry, even in the infrared part of the spectrum, which in some ways James Webb is just very superior for. People are still using Hubble just because there's only a limited amount of telescope time available on all the world's telescopes, so there's a lot of competition for it.
And where is Hubble currently located?
Oh, it's moving all the time. So this is one of the big differences between Webb and Hubble. So Hubble is in low Earth orbit, so it's whizzing around, and that has the advantage that you can send astronauts there and it can be repaired, and it has been repaired and refitted several times. In fact, it was rescued by a repair because there was a problem with its a really fatal problem with its optics when it was first sent up, and they actually did manage to send a repair team there to rendezvous with it and fix it, and it's had service a few times since. But it's in low Earth orbit, which makes it accessible. You don't need a lot of energy to get it there, so you don't need a huge rocket booster to get it there. But the disadvantage of being low Earth orbit is that it's whizzing around all the time. So if you want to actually just stare at a given star for a long period of time, you can't do it. You get a blink of it, and then you have to wait till you come around again and point again. Whereas James Webb is at a position called L2, about 1 million miles away, where it doesn't actually orbit the Earth. It's where the gravity of the Earth and the Sun more or less cancel out. So it just sits out there, and it does drift along with the Earth's orbit. But James Webb can actually stare at a single star or cluster of stars for days on end, with only the slightest adjustment in its pointing.
So
And
James Webb is out there.
James Webb is way out there. It's 1 million miles
Uh,
away, and that's why it was absolutely essential that all of its automatic robotic deployment work flawlessly,
mhm.
because for we have no technology for sending a human out to L2.
Yeah, no,
Maybe
thank you.
someday. And so, the main thing that limits the lifetime of James Webb is running out of fuel to keep it in position, because the L2 position, a million miles away, is it's a little bit unstable. If you put something there, it will slowly drift away and eventually just go into a general orbit around the sun, or maybe so. You do need to use a little bit of rocket fuel to keep it in position. There's enough rocket fuel left to keep James Webb going for about 15 years. And originally, we only hoped for 5 years, but the Ariane rocket insertion was so accurate, it didn't use Webb didn't need to use any of its fuel to get onto station, get onto its position, and so it had enough fuel left over. We can keep it going for 15 years. But if you can refuel it, then you can keep it going for much longer, and you wouldn't need a crewed mission to refuel it. And so they did make some kind of provision for something to hook on, open the gas tank, and pour some more fuel in, as it were. And so if someone develops a way of getting a robotic refueler tanker ship out to L2, there may be a chance of extending the lifetime, assuming nothing else breaks. But it's the fuel that's projected to be the limiting factor in how long it can be used.
Here's a dumb question. Well, I don't think it's dumb, but it might be. What's the idea of making things that we send out into the universe solar powered, since there's always the sun?
Oh, what's the well, actually, it's sorry, wait, were you asking, were you thinking about why we don't have solar powered rocket engines that wouldn't run out, or are you
Yeah,
thinking?
for like smaller craft, like obviously I don't know how small or how large these
Yeah.
telescopes in space are, but my idea is like I think don't we have the technology right now that if we sent something, initially with fuel to get out to where it needs to be, is there a way that we have enough technology to allow these things sort of in orbit or slowly moving across the solar system to use solar power?
Yeah, so it's an interesting idea. We may have that kind of technology for rather small things. So there has been talk of using, say, solar sails for interplanetary probes. That just uses the pressure that light makes when it bounces off of a reflector. There are also these ionic rockets that use electricity to accelerate charged particles that shoot out the back. But those are all very, very low thrust things. And so while we use the solar energy to power the instruments on most of these space probes, at least in places where there's enough solar energy to use that. While we use it to power the instruments, it doesn't have enough power to actually keep it on station with an ionic rocket. That may happen someday. Although the solar sail idea would be a kind of an inexhaustible way, because you don't run out of photons from the sun. You use the photons, the light particles that are bouncing, to push something around. You need a pretty big sail because photons don't produce much pressure, but someday they may develop something like that. But for the ionic propulsion, where you use an electric field to accelerate charged particles, you still have a limitation in that you need some particles to push. That's called reaction mass. So rockets not only need the energy to heat up the fuel and push it out, because rockets work by Newton's law of motion, that you throw something one way, and you go the other way. You have to have something to throw out of your rocket. You have to have some reaction mass. And so if you're sitting out there in the near vacuum of space, there's no resupply of reaction mass. And so even ionic rockets, which could keep going longer than chemical fueled rockets, because they get their energy at least from the sun, even ionic rockets would eventually run out of reaction mass. But probably they could keep things going longer if we had enough solar energy to actually get enough thrust. Right now, the technology isn't there for big things. It's something that people are definitely thinking of for interplanetary probes.
Yeah, that makes sense. It would be, listen, I would have no desire to be on one of those interplanetary outer space adventures. That is not for me. I am very comfortable on Earth, but there are people that would jump on that idea. But that actually leads me to a question that I have. So, obviously, we've talked about the solar system and different planets and so on. But over Earth's history, how do you think carbon has moved through the different systems that we have here? Like, obviously, in space, and as you mentioned earlier, your first interest for science was through the motion and the flowing of water and liquids. But, we have oceans and life here. How has it shaped the planet's ability to sort
So
of go
actually,
through
yeah.
everything?
So even before life, carbon was playing a role in keeping the Earth's temperature hospitable for life. Because even without life, the basic carbon cycle on a planet like Earth with liquid water is that there's a balance between the carbon dioxide in the atmosphere, which then reacts. Carbon dioxide, when it dissolves in water, makes a weak acid, carbonic acid. It was what makes fizzy water taste a little bit pleasant. It's a little bit tangy. If you actually made water fizzy with just nitrogen, like they make some beers actually, if you made water fizzy with nitrogen, it wouldn't taste the same.
Is that what a nitro brew is?
Yeah, nitro brew. Yes, yeah. I think Guinness does that. It makes a different size of bubbles, and actually one of the reasons people do nitro brew is that it doesn't acidify the beer, and so it subtly changes the taste.
Who would
As
have
now,
known Dr. Professor
yeah,
Raymond Pierrehumbert is a beer snob? Who would have known
yeah.
that?
Yeah. Well, actually, I don't like artificially gasified beer. I can't say carbonated because nitro brew isn't carbonated; it's nitrogenated. But I don't like the artificially gasified beer. The real ale like we have in England and Scotland and the UK. Well, it's made with yeast that makes carbon dioxide naturally, and it doesn't have carbon dioxide added to it.
So it doesn't have that
I'll
same
go for a
taste?
pint of Guinness. Yeah.
I don't
Yeah.
drink soda or beer, so I don't know what they taste like, but people are like, "Oh, it has a specific flavor." So it doesn't have that flavor because it's artificially carbonated?
Well, it's different. Yeah, the part of it is that if it's artificially carbonated, then you don't really have as much contact between the yeast, which is a little miniature chemical factory making all sorts of good tasting stuff. You don't have that natural contact between the yeast over a long period of time and the beer. You do need some of that contact even in bad beer because it's the yeast that makes the alcohol. But when you sort of short circuit the carbonation process, you have less of that stuff, and so yeah, so you
That's
you
so
make those.
fascinating. I would have never even known. I would have never even assumed we would talk about this on this
Yeah, yeah.
episode.
Well, it's just there's the same physics, the same chemistry is everywhere, and so the yeast that are making alcohol are also making carbon dioxide, and they're using these ancient enzymes that allow the yeast to essentially combine oxygen with carbohydrates in malt and things like that, but at room temperature. Ordinarily, you have to heat things up to flame temperatures to actually get oxygen to combine with even oil or carbohydrates, whatever. But these enzymes that evolved very early, they actually catalyze the combination of oxygen with organics, and that's what allows us to eat. And so you have your ancient enzymes making use of energy stored in carbon compounds, and it's been doing that for billions of years. But anyway, so in terms of where the carbon goes, so carbon dissolving water makes carbonic acid, and that reacts with the main kind of rock we have, silicate rock, feldspar, stuff like that. The rocks that are made of something like calcium hooked together with the silicate ion, SiO3, silica and oxygen. Silicate rocks are made out of a metal, mostly calcium and magnesium and aluminum, and some silicon and some oxygen. And it's what rocks are made of. If you pick up a rock, most rocks that you would pick up are silicate rocks. But the silicate rocks, in contact with carbonic acid, make carbonate rocks, which store carbon. So that's limestone. So I say most rocks you pick up are silicates, but there's a lot of limestone lying around too. So depending on where you live, maybe the rock you pick up is a carbonate like limestone instead of silicate. But most of what the Earth is made out of, other than its metallic core, is silicate rock. And so there's this chemical reaction is trying to suck all the carbon dioxide out of the atmosphere until it gets so cold because of so little carbon dioxide that the ocean would freeze over, and we wouldn't have formation of limestone from rain, and a little bit would still form in the ocean floor, but that's inefficient for some various reasons. So this reaction, which is called the silicate weathering reaction, is trying to suck out all the carbon dioxide from the atmosphere. But the reason we don't freeze out is that the plate tectonics subducts. It sucks down all that limestone into the hot interior, where in a process that's sort of like making cement, it decomposes the limestone, and then the carbon dioxide comes back up through volcanoes. And so the Earth for billions of years has existed in this equilibrium between the amount of carbon that is sucked out of the atmosphere by reaction with silicate rocks making limestone, and then the cooking out by volcanic processes. And there's even a temperature dependence that tends to keep the Earth at the temperature where you have liquid water. It's called the silicate weathering thermostat, and that's been operating almost without fail for 4 billion years. And but the amount of when life came along, life was able to do something else. Life was especially photosynthetic life that can use carbon dioxide and solar energy to make carbohydrates, energy storing carbon, can turn carbon dioxide and various other traces into organic carbon, and releases oxygen, which we can breathe. Okay, life was tapping into various other things to make organic materials earlier, but it was once life evolved the ability to tap into solar energy that life was really able to take off in a massive way. And so you might wonder, I mean, once life starts turning all of our carbon dioxide into organic carbon, why don't we just freeze over? And the reason is that there's a lot of energy in that organic carbon. It's like oil or coal. In fact, it's where oil and coal come from, ultimately. There's a lot of energy in there. And so once you have oxygen around, other things evolve that will eat that organic carbon, just like we do, and turn it and combine it with oxygen and reconstitute the CO2. And so that's a fast carbon cycle. And that relies on biology. That carbon cycle is so fast that it's more or less closed. The amount of carbon that gets turned into organic carbon by life each year almost exactly balances the amount of organic carbon that's eaten and turned back into CO2. And that tiny little trickle that escapes that process and gets buried, that's where our fossil fuels come from. And that's been happening for billions of years. It's especially been happening in the last 2 billion years when there's been oxygen around, when life was really going like gangbusters. But so all this carbon that has built up in fossil fuels over billions of years, we're digging it up. It's been safely sequestered down there where it can't get it, where oxygen can't get at it. This billion-year store of carbon made by this little trickle that escapes this cycle of organic carbon production and respiration. That tiny trickle that made our fossil fuels, that took billions of years to accumulate. We're digging it up, and we're burning it and turning it back into carbon dioxide in a matter of a few centuries, maybe less than a few centuries.
Yeah, just
And
like
that's why
maybe
we've got a
200 years.
yeah. So that's why we have a big problem with global warming. We as humans, with our technological capabilities, have massively disrupted the carbon cycle that has been keeping Earth habitable for billions of years. And it's all CO2. It's all CO2.
Yeah, I would say the Earth is something I've thought about since I was a small child. The Earth is basically like a cell. It's just a self-regulating organism
Yeah.
that takes care and
Yeah.
produces everything that it
Yeah.
needs as long as it has the energy from the sun.
Yeah.
But that is a good point. You know, we've been pumping up all of this stuff. Again, like you said, a billion-year storage of carbon that has been untouched at the bottom of the earth below, these tectonic plates. And, well, I don't know if it's below the tectonic plates, excuse me. Not the.
Well, the tectonic plates get sucked down into the interior. It is the
Mhm.
tectonic plates, and they get sucked down. The oceanic crust gets sucked down into the interior where it's
Mhm.
hot.
Yeah,
And
and
that
we're
makes
just taking all of those fossil fuels out now. And what would you say is a good solution? Obviously, we can do our best, like planting more trees and trying to do better green infrastructure that makes sense, that's actually usable as both an affordable and long-term scheme and plan. But what do you think? What's an idea that you have that you think we could use to combat all of these pollutants that we have currently going on?
Yeah. Well, there really is only one solution, and that is to stop burning fossil fuels. That's decarbonizing the economy, and planting trees. There are ideas to try to suck carbon out of the atmosphere. Planting trees is good for biodiversity. It's good to avoid deforestation, but there's not enough room to plant enough trees to really account for more than a tiny fraction of the carbon dioxide we've stuffed into the atmosphere. And this process, these natural processes that take carbon dioxide out of the atmosphere, are really slow. So even after we stop burning fossil fuels, it will take thousands of years for the natural system to recover, for the carbon dioxide to go back down to the pre-industrial, the natural level. And so we are in this bad situation that every year we continue to burn fossil fuels, we ratchet up the setting on the thermostat. That would most likely last for thousands of years. And so the only way to stop that process, the only way to stop continued warming, is to stop burning fossil fuels. And we have the technology to do that. My colleague Susan Solomon at MIT has a wonderful book called Solvable, which makes the case that not only do we have all the technology to replace our energy systems with carbon-free energy systems, but there are even economic incentives that would favor that if only policies would get out of the way of artificial subsidies of fossil fuels and artificial barriers to building renewables. The technologically, it's a message of hope. But I have this article that says there's no plan B for the climate crisis. People are hunting around for something we can do if we don't decarbonize. But the only thing we can do if we don't decarbonize basically is to suffer. And the quicker we decarbonize, the less suffering there will be.
What's one thing from that book that you say we could apply ASAP? If in an ideal situation, what's one thing that, or maybe an idea that you have or that you've thought about?
Oh well, photovoltaics. Well, it's basically building more photovoltaics and wind. That's
Now, what
that's
is
some of
that?
it's solar cells, photovoltaics. They're just it's just solar power. The price of solar panels has come down dramatically, and actually there are hopeful signs that places like China. And India, which are some of the biggest carbon emitters in the world, are actually going along pretty fast. Or Pakistan, especially, has had a big commitment to solar cells, solar energy, and then wind. Wind and solar cells, solar energy are cheaper than building. They're cheaper than building coal-fired power plants by a long shot. And they're no more expensive than gas-fired power plants, especially at the price of gas in Europe, natural gas, so-called natural gas in Europe. So all the economic incentives are to build more of these things, but there are barriers. Like you need to have enough electricians, construction workers. There are costs of raw materials, capital costs up front, which will more than pay themselves back, but the money has to flow in the right way. And then energy efficiency, in every possible manifestation. And I do think eventually, although nuclear power, the main problem with nuclear power, as I see it now, is not environmental,
It's the
because it's less
waste.
The waste. There are solutions for handling nuclear waste, and carbon dioxide made by fossil fuels is a kind of waste that's much harder to deal with. And much more damaging over long periods of time than the nuclear waste, which could be confined. So the main problem with nuclear is that right now, for whatever reason, nuclear is just really really expensive, and it's kind of a mystery why nuclear is so expensive. It's gotten more expensive since 1970 per unit of energy made, and so there's no way we're going to build our way out of the climate crisis by building the kind of nuclear plants we're building now. And so the hope is that if people manage to engineer these small modular nukes, smaller, easy to manufacture nuclear efficient plants, they will bring down the cost and lower the time it takes to build them, because they can be sort of mass produced and just trucked to a place and plugged in to the grid. But we don't know if that engineering is going to work. But that's in there somewhere. But right now, just with wind power and solar power, we could actually be doing a whole lot.
Hmm.
And so we can certainly be doing a lot more than we're doing now, but finding ways to get the barriers to deployment out of the way is the key thing. And that's something in the realm of politics where I couldn't actually say what the magic bullet is there to accelerate deployment, and getting these completely artificial subsidies for fossil fuels and completely artificial barriers to deploying renewables is something that has to be done. And then what's going on in the United States is sad and tragic and dangerous, but uh, what happens in China and India and Pakistan, well, especially China and India, what happens there probably will have more leverage than what happens in the U.S., because right now China and India are still relatively poor countries, but they're on a track to become as rich as the U.S. And when people get richer, they tend to use more energy, and we have to make sure they also are on the track to that new energy that they use as they get richer is renewable energy. And China is very firmly committed to this. India, uh, but they're sort of moving in that direction just because of the environmental impacts of burning coal, even locally, not through global effects like global warming. But
Hmm. Listen, at the end of the day, we all just want solutions that work and that,
yeah,
make everybody healthy and help keep this planet healthy and happy. And so, as
yeah.
we're winding down, Professor, thank you so much for being here. I have one last question I want to ask you. We like to ask each of our guests this, but something, even if it's not related to your field, what's something, a topic or a passion that you have, or something that, keeps you interested that you'd like to share with the audience?
Well, I have to. It's hard to pick one. It's like saying which is your favorite child, which is not
It doesn't have to
possible.
be just one. You could list off a
Yeah,
few
yeah, but
things.
that's why I will give you sort of three. So one passion I have. It's not a question. It's just a passion that keeps me going in the face of the excitement, with sort of the stress of doing science and of everything that's going on in the world. Is I play folk music. So
Okay,
uh,
nice.
Swedish, Finnish, French, Scottish, and so forth. I mostly play accordion and melodeon. And Oxford has a wonderful folk music scene, and a lot of my best friends are from the folk music scene here. And just being able to go to a pub on a weeknight and play some Scottish tunes until midnight, that's a big part of what keeps me upbeat in
Hmm.
terms of. And even science itself has its frustrations. It's a exhilarating thing, but it can be a stressful thing too. And I'm not talking about the stress of just applying for grants, but just batting your head against a problem you feel you're inadequate to solve. There's the stress and there's the excitement, uh, uh, but so the folk music is a big part of what keeps me on an even keel, and allows me to work pretty hard the rest of the time. But in terms of so two questions though, we talked about the origins of life, and life emerged very quickly. on Earth. But there's this period after oxygen first emerged, which we like to call the boring billion. And there was a lot going on at the beginning. We had this global glaciation. And then at the end, about 1.5 billion years later, we also had a lot of global glaciation, snowball Earths. That we call that the cryogenian. But in between, there's this 1.5 billion-year period when nothing much seemed to be happening. But during this boring billion, we only had single-celled life. The complex cells started to evolve. Cells with a nucleus and separate DNA, they started to evolve. We sort of know how that happened, but they didn't do very much. And so in terms of whether the universe has a lot of complex life like us, life that can talk to us, comes down to whether this boring billion was unusually short or unusually long. Maybe were we unlucky or were we lucky? Because if the boring billion had been the boring 4 billion, we run past the time when the Earth is habitable, because we turn into Venus in another 500 million years because of the sun brightening, even before the sun turns into a red giant.
Mm-hmm.
And so one of the key questions to whether there's intelligent life in the rest of the universe is just what made the boring billion so long? What was the pacemaker? And that's something, it's a really hard question because it's an interplay of everything from biology, chemistry, evolutionary biology, and geology. But that's a question I would passionately like to know the answer to. And we're not close. We're not anywhere close to knowing the answer. But there's one other thing, which is more in the humanities. So
Let's hear it.
And so Aristotle wrote a number of brilliant books, and some of the books, like his book on physics, is very outdated. It does not really make contact with any modern physics. But he wrote a very intelligent book about meteorology, Meteorologica, in which he actually reports experiments and things like that. So deep thinking about meteorology. He knew that water could evaporate into the atmosphere and that it leaves salt behind, stuff like that. Very keen observations. So I admire Aristotle as a thinker. He wasn't just making stuff up. And then but in his theory of drama, he has one book about tragedy, which has survived, which is where a lot of our notions of what are the elements of tragedy, just like the periodic table, is the elements of what makes us up. Aristotle really put together the first ideas about the elements of drama that make a tragedy. But I like comedy quite a lot, and it's known that he wrote a book about comedy, but that's lost. And so I would love to be able to peer back in time and read Aristotle's book on comedy and see what his thinking was about what made the essence of comedy. I don't read Greek, so I would have to get one of my classics friends at college to help me with that. But that's I would really love. I've always wondered what was in his book about comedy.
That's so fascinating. It's so many cool things that each person loves. Professor Pierrehumbert, thank you so much for joining us today. This was super fascinating. I learned a lot and learned so many cool things I would have never even thought about. So this has been a pleasure. Thank you. Thank you to everyone for tuning in and listening.
It's been a pleasure talking to you. I really enjoyed it.
Absolutely. Thank you.